Our next speaker is Arnab Pal, and he will be talking on target search optimization by threshold resetting.
Okay, so thank you very much. Good afternoon, everyone. So I will start by thanking the organizers for holding this meeting for last several years and letting the community grow over here. And of course, the benefits are there. So this short presentation that I have over here is on a recent preprint that we posted on archive based on this one. It was done by my student Arup, who is in the audience, and by Satya Majumdar, who is in Paris. So let me just start, because there were not many talks on resetting, so let me just give a brief introduction to the resetting. So it's all started with this, this classic paper by Satya and Martin Evans, like a decade back or so. So where they were just interested in looking into a very simple system. You have a diffusing particle, and what you do is, let me try again. So you have a particle which is basically diffusing, and then you have an external clock, and it's a random clock, let's say. And then when that clock occurs, what you do is you essentially take the particle wherever it is, you teleport it back in 0 time all the way back to its initial position. This is like a very simple setup. So this is what they started with. Since its inception, actually, the field has grown exponentially, and we have seen like many, it's going beyond diffusion. We have seen like many different applications all the way from chemical reactions, ecology, operation research, so on and so forth. There is no scope for me to give details, but if you're interested, there are several review articles which you can take a look at. So just a summary of like more or less the way to understand like a very brief thing would be as follows. So just imagine that you have like you are doing an experiment with a diffusing particle. So it's like in 2D. So what you do is let the particle diffuse in 2D, and then once in a while you use some optical trap essentially to bring the particle to the original position, right? So this is exactly how the trajectories will look like. And what you're interested in is in the what happens in the large time, right? So if you look into the long time, unlike the diffusion, which never equilibrates or goes to a time-independent form, so here what the first take-home message is the system essentially reaches a steady state. So that what you see in here, and then also another very interesting aspect is that if you're looking to the first passage problem, which is going to be the central issue of this presentation. So, so unlike the pure simple diffusion problem, what people can show that the mean time essentially goes to infinity without any this kind of mechanism. But if you sort of intrude the dynamics with this resetting mechanism that I showed, what it does, it basically renders the mean first passage time finite. So these are essentially the two key messages from here. The way to understand this problem is what resetting does. It essentially, every time you reset, it allows your system essentially to explore new trajectories, and this way you can, what you can do is basically you can eliminate some sort of errant directions which you don't want to go along. So this is essentially the summary of this. And then I would not go into the details, but if you are interested in why and when resetting works, there are also some very quantitative understanding of these things. So if somebody is interested, I can talk about it later. So the thing, all the things, what the most of the studies till this paper, they were all focused by this fact that there is an external clock and it tells you when to reset, right? So this clock is not coupled to the system. Okay, it's not coupled to the system degree of freedom. But then there is this paper by C. Dredner who introduced this concept of threshold resetting, and they called it a first passage resetting. So what happens is like you have a diffusing particle, so in the terms of diffusion, let's say, and whenever it reaches a certain threshold, like L, then you basically reset the particle, okay? So there is a key difference between the previous case and this case, okay? So let me just try to explain on that. So traditional resetting, what happens is this time scale is externally decided. So it is not coupled to the system degree of freedom, and somewhat there are a lot of mathematics. There is a very nice structure, renewal structure that you can use here, and using that you can solve many problems. But on this case, in the other hand, the one threshold resetting, it is essentially event driven, because the system, the position of the particle, let's say the particle has to reach L, and only when it reaches to L, and then only you can reset the problem, okay? Reset the particle. So this is the way, this is quite different, these two setups. And we were interested in understanding, so just to give you a cartoon, like let's say, okay, so I think I have to press here. So just to visualize this, so you have like a particle which is diffusing, and then exactly when you reach the threshold, you reset it back. Okay, so this is very simple way of doing it, but it has a very distinct mechanism than the previous, most of the problems with stochastic resetting. And what are the key questions that people were trying to understand? So what happens to the long time limit if you wait for a long time, whether the system reaches a steady state? So this is exactly what was studied in this first paper by Sid Redner in the 2020 paper, and he showed that for a simple diffusing system, the system doesn't reach a steady state, which is in contrast with the classical resetting where system reaches a steady state. And then what we were interested in a couple of questions, actually the parallel question, which is the first passage problem. So imagine that you have something like this, you have a threshold, but then there is a global target which you would like to reach. Okay, this is the classic first passage problem. You have, what we have here is we have like n number of searchers. So everybody like starts at the same point, let's say starts diffusing or does some sort of stochastic dynamics. And at any point of time, if one of them reaches the threshold, you basically reset all of them together to the initial condition. Okay, that's the game. Okay, now what happens in this way, and Sanjib touched upon this in the morning, like if you have many particles and if you reset them or do some collective mechanism, so there is a underlying structure called CIID, which is basically some sort of correlated IID random variable, which essentially creates some sort of a long range correlations because of this simultaneous process. And we were interested, what is the effect of n number of agents? Because if n agents, they are somewhat becoming correlated. And what is the mean search time? Can you come up with a general formalism beyond diffusion and stuff like that? And what kind of optimization we can talk about, like similar to classical diffusion? Okay, so I will skip this busy slide over which talks about the formalism, etc. Or maybe what I will do is I would like basically to show one particular example that we worked out completely. So what we have here is the stochastic particles, like it can be any dynamics. So diffusing dynamics is something which you understand very well, but let's just also assume a different type of dynamics where, let's say you have ballistic searchers. These ballistic searchers, what they do is like they take random velocity when they start off, okay? So randomized initial velocities, you start off, you hit the target. If you hit the threshold, you reset, and the main goal essentially to find the global target. And when we plot it after calculating the mean time as a function of u, and then n is basically the number of searches, what we observe is that this mean time essentially is globally optimized at u equals to 1. Okay, so u equals to 1 essentially would be, u is the scaled variable, which is basically the, if you start exactly at the resetting threshold, if all the particles start exactly at the resetting threshold, that is apparently the most optimized behavior, right? And if you think about it, it's very non-trivial, right? Because you're starting at some point of time, you immediately reset, but your aim essentially is to find something which is far away from you, right? So how that can be an optimized behavior? So let me just talk about that particular limit here. So what happens here? So yeah, so I will finish off very soon. So what happens in particular this limit where you see the global optimization is that you have, of course, because you start exactly at the reset threshold, you reset many times, right? So the frequency of resetting is too high because you're immediately resetting, but also it doesn't take, because the particles actually cannot go at all, so the time it takes also to reset is almost 0. So the number of resetting event is high, but the time it takes to reset is also 0. So essentially you're waiting for those kind of collective effort where all the particles essentially will have some sort of a velocity where all of them essentially will run towards the target, okay? So this probability, of course, this probability is very low, but this actually can happen. And when this happens, you'll see the system essentially will explore the phase faster and will find the target. And in between, of course, if you just slightly move away from there, then this, of course, there is a constant, now the number of resetting events also will be high, but the time consumption is also high, so the mean time essentially keeps on increasing. And then the u equals to 0 limit, where you see the divergence, essentially this is a case where the resetting threshold is quite far from the target, and here the particles can have, because they are sampling velocity randomly, so they can have equal probability to take positive or negative velocities, and if they take negative velocity, essentially they run away from the target. So it's also the case where you see is exactly the mean first passage time diverges. So unlike the classic resetting problem where you see a very nice global minimum, and also this kind of limit doesn't really exist, at least especially barring a few cases. In this resetting, in this threshold resetting, you see some very nice optimization behavior. And you can also calculate some limiting behavior exactly via some non-trivial calculations. Okay, so because I have run out of time, so I just want to actually conclude the talk by giving the motivation of this problem rather. So what happens, like when we're looking into this problem, and we understood that actually in nature there are many natural processes which are governed by threshold triggered events. Meaning, like you have some sort of a dynamic which reaches some sort of a criticality, and when that happens, so system either can go to a different state by some transition, or there can be some degradation, or there can be some failure. And then there are like plenty of examples, and the most fascinating examples actually come from neuroscience. This fire neuron models, and actually the ones that we recently found out is basically the movement of the eyes is called microseconds. So I can discuss with you in the break, during the break. And then naturally there are also other systems, for example, these financial strategies and all, power management, where all these kind of things always happen. Like whenever you reach something, system collapses. So motivated by this, I think we proposed a new class of first passage problems which are driven by threshold resetting, and we hope that it will also trigger some new interest to the community. Okay, with that I will stop. Thank you.
Thank you, sir, for the interesting talk. We have time for one or two questions from the audience.
So what we understand, like currently we are just doing some analysis, it seems that the time to reach the threshold for the diffusing particle, that's a power law. But now you can ask for general distributions. And what Arnab found out that if the mean time, if you can ensure that the mean time is finite, so it seems that there will be a steady state. But there is no general theory for this. So we are working on this, even for single particle level.
Any more questions?
Hello. So you are resetting all together at times,
Yes,
all the particles.
All of them.
So if someone hits it, you reset. And like, can this be optimized if you like? Satya has some work, I think, like if they all reset at random times, they just hit and singly they just reset.
Yeah, so what he has is the traditional resetting.
Yeah.
He has that, like you have a clock.
No, you let n particles evolve, and they reset when they just hit the target. It hit the threshold. Yeah. Not all the particles are reset together.
No, I think that's
that not be optimized.
No. I don't think that is exactly this problem.
No,
they don't have a threshold. What
okay.
they had is like the particles. They have the classical resetting. So you have many particles, and if there is one time, you reset all the particles. Yes. Oh. Yeah. For that you have a steady state. Okay. That has what Sanjib discussed a bit.
They have steady state on interacting particles. Yes. Thank you.
Any more questions?
Can we? So you when you mentioned threshold, can the threshold be on any? Can be defined for any observable, or is it just position or?
So for example, this is where we looked into the position, right? Okay. But like for example, this fire neuron models, right? So there is essentially the voltage which fluctuates. So when voltage reaches a threshold, so then that governs essentially the threshold trigger thing. So it's not related only particular to position. Yes.
Any more questions in the audience?
First of all, so we at least here what we do is basically we have a set of threshold which is fixed at L. Okay, so you see, if you see this one, so maybe here you see that this is a fixed threshold, right? And the optimization is with respect to where you want to start with. Like in between, you can start from anywhere, right? That's your scaled variable. Let's say U. That is like you can start from anywhere in between, and then you want to find whether the mean time can be optimized with respect to the initial condition, some sort of a So in this case, we are not, but some of the examples that we looked into, so there are a lot of evidence actually how to design the threshold or how to give a numerical value to the thresholds. Yeah, people have lots of done lots of research actually to find out this threshold and all, mostly from experiments. Yes. We have not done it. We have, for us, it's fixed. Okay.
It's a steady state of what?
Position distribution.
So the particle would ultimately remain in certain distance away from the two bars.
So if you, so for example, so this problem is not the steady state problem because there is a global target. So essentially the particles will go and essentially will get absorbed, right? So now imagine that you didn't have the target, right? So the particle goes and hits the threshold, right? And let's say that you look into the process for a very long time. After a long time, what happens to the position distribution? So that doesn't reach a threshold, at least for this process. For diffusing particle, it doesn't reach a threshold. But if you like somehow manage to, doesn't happen, reaches a steady state, just that's because that for the diffusing particle to reach the threshold follows a power law. There is some sort of an internal thing. But when you say threshold, meaning like they have some distribution, the position has some distributions, time independent steady state. If not, I will explain later.
By tuning the threshold, can you make sure it converges in any way? Hi, so sorry.
Yeah.
Can you make sure it converges by any way by tuning the threshold or something?
Converges, so exactly what converges?
Convergence isn't like that the process will end, that you will reach like your target.
So the mean time.
The mean time being
so
finite.
Mean time, here it is for especially the kind of processes you look at, here it will reach, right? Because there are, in effect, there are two boundaries here. The threshold is a boundary, that is also another boundary you have put.
Any more questions? Okay, if there are no more questions, let us thank the speaker once again.
Thank you.